Hello and thank you for watching my video on estimation and confidence intervals. Here we will learn how to estimate the parameters of a distribution. So take normal looking data and you would like to estimate the parameters mu and sigma square in a normal distribution using your data. How to do this with and without Excel. Let's get to work.
We see two types of estimation methods, point estimation and interval estimation. So what do I mean by this? Here is an illustrative example. In the US, on all new cars, there is a fuel economy estimate that is displayed on a window label. This is required by the Environmental Protection Agency, EPA. And so this is an old window label dating from 6 years ago, but I think it's a good illustration. The new ones are not such a good illustration for confidence intervals. So what I want to emphasize. So if you look at the on the left, you see this 18. 18 is the miles per gallon of this particular car. And below this 18, you can see the expected range for most drivers, and it's between 15 and 21. So 95% of drivers for this particular car manage to do between 15 and 21 miles using a gallon. And on the right, you see the same thing for the highway consumption. So the ball number 18 basically corresponds to the point estimate of fuel consumption, and this expected range is the confidence interval. So how to construct these confidence intervals? Well, let's start the point estimation already. So assume that we have observations. I denote them by x1, x2, etc. until xn, n being our sample size. And assume that they are from a random sample coming from a distribution denoted by lowercase f, p denoting the parameter of this distribution. If it's a Bernoulli distribution, then we have a probability parameter p, right? If it's a Gaussian distribution, we have two parameters mu and sigma square. And we would like to estimate the parameters mu, sigma square, and p, right? Now, what is a point estimator? A point estimator is just a function of the random sample, x1 through xn, any function of the random sample. Now, a point estimate is something that you apply to the sample. If you have observations of your random sample, then you just plug in your point estimator and you obtain your point estimate. And we will denote by p hat the estimator of the parameter p. I will not distinguish between point estimates and point estimators because it would be too cumbersome to have too many different notations. And I will each time emphasize whether it's an estimate, a number, or a random variable. Now, let's be concrete. Let's take a random sample from a Bernoulli distribution in which we have a parameter p that we would like to estimate. Now, any function of the random sample would be an estimator of p. Denote by uppercase x bar the mean of this random sample. Now, this mean is already an estimator for p, but I can invent all sorts of weird estimators. Any function of x bar or any other function of the xi's would also be an estimator. Let's consider already these two functions of my random sample. These are estimators of p hat and p tilde. Now, which one is better? In other words, what does better mean? We already want to have a goodness of measure somehow for an estimator. How well does an estimator estimate a parameter? How to answer this question? Well, we have this measure, the so-called bias. Well, first of all, let's start with what an unbiased estimator means. It means that the expected value of my estimator is equal precisely to my parameter of interest, p. Now, if now we can define actually what the bias means. The bias means the difference between the expected value of my estimator and the parameter of interest. So let's draw this. What I mean by this is that the bias is bias of an estimator P hat is the expected value minus the parameter of interest. Now we can show that in the previous situation, the previous example, the P hat is an unbiased estimator and P tilde is a biased one. Now, where does it come from? Actually, we can be much more general. If you take a random sample from any distribution, but such that the expectation is denoted by mu and the variance is denoted by sigma square, then the mean of the random sample is an unbiased estimator of the expected value, and the sample variance of the random sample is an unbiased estimator of sigma square. Now, proofs are posted on my website, and here I will skip the proofs to gain some time. Now, using these results, since we have here the mean of the random sample, and I know that it's an unbiased estimator of mu, I can apply it to my previous example, and I know that here in the Bernoulli distribution the expected value is P, so this will be an unbiased estimator of my parameter P. P hat is an unbiased estimator of P, and hence P tilde will be a biased one. Now let's see concretely an example. So yes, this is something that I already emphasized, right? P hat, I just said that it's an unbiased estimator of P, but now I can also apply the same result to a normally distributed random sample. The mean of my random sample in a normal random sample is also an unbiased estimator of mu, and this sample variance is an unbiased estimator for sigma square. Let's be concrete. Let's take two data sets. Here I have the flip of a coin. I flip a coin 250 times, and let's assume that 140 times I obtain heads. Now, assuming that we have the flips come from a Bernoulli distribution with a parameter P, let's estimate the probability P of obtaining a head after one flip. Of course, we'll use an unbiased estimator, the one that we already created above, right, P hat. And let's calculate the point estimate associated with this estimator. So here it is. We simply let me go back to my notes here. To calculate the point estimate, well, I simply need to take the sample mean of my observations. But what is the sample mean? Well, it's the sum of my observations, right? I going from 1 to 250 divided by the total, right? 250. And I know that here I have ones and zeros, and in total I obtain 140 heads, right? So in total I have 140 divided by 250. So this makes me 0.56, right? And so this is a point estimate of P. Now this is for my first example, right? And my second example, in my second example, I have a data set of, we have the work hours, weekly working hours of junior executives. And the data set, it looks like this. We have, in total, we have 50 junior executives, and we have the weekly hours of these junior executives. If I draw a histogram of these data, I can do it with data analysis, but I need the bin sizes. So let's compute. I know, well, the range of my data is, well, it goes from basically 48 to 60 to 75 basically. So I will construct on bit sizes starting from 48, and let's cover the entire range of my possible values. This is already out of range, and let me draw a histogram here. So by clicking on data and then data analysis, I select histogram, here it is, and I enter in my input range the A column, and then in the bin range I enter my D column. That's right. And then I would like the chart output, and I would like to see my output on starting this starting this case, right? Here, this cell. Here you go. I have my histogram. It is nicely, we have a nice bell-shaped distribution, and assume that this is precisely a normal distribution with an unknown parameter mu and variance parameter sigma square. So we said that we can estimate in an unbiased way both mu and sigma square. For mu, I need x bar, the sample mean. So let's calculate the sample mean and the sample variance, right? Here it is, the sample mean. How do I do it? I write average, and I specify the A column. I enter my A column. So here it is. This is my estimate of mu. And here I will write the sample variance. In Excel, you simply write var, V-A-R, and then you enter your column. And I have my sigma square estimate, right? So this is my mu hat, and the following one is my variance estimate. So for mu hat, I have 60.23, and for sigma square, I have 35.415, right? That's my estimate for sigma square. Now, it is not very likely that the sample measure that I just calculated exactly matches the population parameters. So these are simply estimates what I just calculated. These are I estimated the expected number of weekly hours, working hours of junior executives, and the variance of the weekly hours, right? But I only had a sample of 50, right? So it's not very likely that the 60.23 is the exact population mean for all junior executives in the world, right? So let's provide another way of estimating a parameter, something that is more likely to be true. And for this, I would like to provide actually an entire range of likely, of reasonable values for the expected number of hours for working hours for junior executives. We will do this by providing confidence intervals. This is how we will increase the probability that our assertion is true. So, of course, we will never be 100% confident that our parameter will be inside our interval that we'll provide, but we will try to be our best and to reach, to be very close to this 100%. So concretely, we will try to construct an interval that provides something like 95% or 99% of reasonable values. So in other words, we would like to stretch out this number. So far, we just provided one number for the parameter, right? For example, for mu, we provided x bar. Now we would like to stretch it out to x bar plus minus something. Why do we do this? To be more confident in our assertion, right? So, for example, if I take a random sample, a tiny random sample of just with 4 elements in it, so I have x1 through x4, I assume that they come from a normal distribution with parameters mu, and to be simple, I say that sigma is actually known is equal to 1. Then x bar plus minus 1 is an interval estimator of mu. And plugging in our data by using for example, our junior executives, by using concrete numbers, I will provide an interval estimate of my parameter mu. We will assert that our mu is inside this interval. Now, the probability that an interval estimator of mu covers the true parameter of interest mu is called the level of confidence. And if the confidence level of an interval estimator of mu is 1 minus alpha, we would like to be something very large. So alpha is typically something very small, but let's be general, let's denote it by alpha. So if this confidence level of an interval is denoted by 1 minus alpha, then the corresponding interval estimate is called a 1 minus alpha confidence interval of mu. And we will denote it by Ci, emphasizing the fact that it's a confidence interval of the parameter mu, and the confidence level is 1 minus alpha. So now we would like to calculate the confidence level of the interval estimator in the previous example, but we first need to investigate the distribution of x bar, right? Otherwise, I cannot say anything about the confidence level, and I cannot say anything about the probabilities. And for this, I need a theorem. So by chance, if we have a random sample from a normal distribution, then the sample mean of the random sample mean is also normally distributed, and miracle, the mean parameter is also mu, but the variance changes. It decreases. It goes to sigma squared divided by n. And now, another nice result is that we can standardize it, meaning that I center it, I subtract mu, the mean parameter, and divide by the standard deviation. Standard deviation is the square root of the variance, right? Then I get a standard normal variable. Now, by using this result, now I can finally calculate the confidence level of my interval estimator that I provided in the previous example. So let's calculate this confidence level. So let's calculate this confidence level for the interval estimator in the previous exercise. So I would basically like to calculate the probability that mu is inside x bar plus minus 1. And I can rewrite this probability as the probability that mu is in between x bar minus 1 and x bar plus 1. And I can still rewrite it in another way. I can move x bar in the middle, and I end up having what? Well, mu minus x bar is in between minus 1 and plus 1. And I can change the sign here. I can write it as x bar minus mu. You will see that it will be more convenient later on. And actually nothing changes, because by changing the signs of minus 1 plus 1, I will end up having the same interval. The only thing that changes is the ordering of x bar minus mu. And now, I know that the xi's are normally distributed, and from this proposition, for a normally distributed random sample, I actually have this nice result that x bar is also normally distributed, and the standardized version is also standard normally distributed. So, to summarize here, I have what? Here I have that the xi's are normally distributed with mean parameter mu and variance equal to 1. So x bar is also normally distributed with mu as mean parameter, and variance, since n is equal to 4, here n is equal to 4 in the previous example, right? I had 4 observations, right? So then sigma squared divided by n is just 1 divided by 4. And as a result, here I almost have a standardized random variable. I just need to divide it by the standard deviation, which is the square root of 1 divided by 4. And I get what? I get, in the middle, I have a standard normal random variable by using this proposition that we just saw. And z is in between what? Here I have 2 and here I have minus 2, right? So z is between minus 2 and plus 2. And I can still rewrite it as the probability that z is less than or equal to 2 minus the probability that z is less than minus 2. And now, how can I rewrite this? Well, if I draw here a standard normal distribution centered at, so at 0, then the area below the curve, below the PDF, before minus 2 is the same as the area after 2. So basically, if I want this yellow here, this is the yellow area on the left, but it's the same as the yellow area on the right. And the yellow area on the right is 1 minus the hatched area here. And this is precisely the probability that z is less than or equal to 2. So at the end of the day, I have twice the probability that z is less than or equal to 2 and still minus 1, right? Now, how to calculate this part? Well, either using a z-table or using Excel. So here I have a z-table in which I have the red highlighted area on the left is reported in the table, and this z, which should be actually z star, is reported in the highlighted yellow areas. So I look for 2 in this column. I look for 2. I find 2, and my second decimal is 0. So I end up having this this probability, this area in the red left area. So 0.9773, 9773, and I let you double check that this actually provides a 0.9546 as confidence level. Now, using Excel, how to do it using Excel, how to calculate this probability? Well, I open Excel and I write equals norm S dist, and I enter 2. S dist like standard normal. Without the S, it would be just a normal distribution, and we should specify the mean and the variance. Well, I get 0.97725, so basically this value here, but Excel provides a more accurate value. Now, this is the okay. We just obtained this confidence level. So if I have now a sample, say that I have a sample, so concrete values for the x's. So that's a sample. I could calculate finally a confidence interval for mu of which level? Well, this is the confidence level. We just calculated it, 95.46%, and it would simply be x bar minus 1, x bar plus 1, or we can rewrite it like this, x bar plus minus 1. That's a common notation for confidence intervals. So now, how to do it in general, because here we just considered for a particular sigma which was equal to 1. Well, you can see it in another video in which I cover confidence intervals for mu assuming normality, and yet another one, confidence intervals for mu without assuming normality. And you can find the course material on this website. Here it is, the website where you can find this course material and the lecture slides. Thank you very much for watching.